All right, so good morning again. We want to pick up today, really challenging topic today, I'll be honest, right up front. It's a challenging topic, and we'll probably be on this same topic again next class period, all right? So not a rush to feel like you have to have it mastered after what you see this morning. I've printed out for you 3 of the tables from the textbook for those of you who don't, have the text with you on a daily basis, which is fine, but that's why I wanted everybody to have these 3 little charts, so we'll reference them. They're kind of out of order, just so I could get them to fit on one page back to back. If you notice the numbering, they're tables 4-6, 4-7, and 4-8. 6 and 8 are on one side, 7 is on the other side. Okay, so. Last class, we learned a little bit about the elements of symmetry and assigning molecules or structures to their different point groups. And today we're going to dig deeper into what the mathematical constructions or concepts are associated with grouping molecules together, finding their like elements of symmetry, and what the power of doing that is, okay? So this begins on, if you're trying to reference stuff in the textbook, it begins on page 90, section 4.3 of our text. And that's where table 4.6 is laid out. So on the back of your handout, or the whatever side's the back, but there's a small table that says the properties of groups. So last class we learned a little bit about what some of the groups were. So today we can see what some of these properties are. When we put molecules together in groups, okay, so this is table 4-6. We'll kind of rebuild it. This is important info to make sure we're starting to remember it. Every group, or each group, contains what's known as identity. E is the symbol for the identity operation. All right. So every molecule or every point group has this identity operation in it, and this is really for the mathematical completeness. All right. Each operation has an inverse. Okay. So every operation has an inverse that, when applied, gives E, identity. So, you do something to the molecule, then there's got to be a way to undo that. That's going to be the inverse operation of it. Okay? This inverse must also be a member of the group. Okay? The product of any 2 operations of a group must also be a member of the group, meaning another operation of the group. Now the word product here is a little tricky. You'll understand what I'm talking about and when we start to get into the matrix representations of operations in a minute. But so the product, to perform 2 successive operations, that's really what that means. All right, the product of 2 operations. So if you perform any 2 operations of a group, the outcome must be the same thing as performing 1 operation of the group. There's some other member of the group, in other words, that could have done that same thing in 1 operation. This is what this rule just tells you. Okay? All right. And then the last one is that the associative property must hold. Okay? So associative is how you group things, right? Meaning, if you had A operating on the product BC, that would be the same as AB first, and then operated on C. So it doesn't really matter which ones you pair, okay? The order, you're going to get the same result, the same outcome. All right. So hearing terms like this about multiplying things, the product, right? This all leads to the next big idea associated with group theory, which is the fact that we use matrices to help us represent what's happening in symmetry operations. Now, my recollection is that matrices are covered most thoroughly in a math course that I don't think is required as part of the chem curriculum. That is the linear algebra course is when I took it. But I'm not sure. Is it part of the math for chemists and mathematicians course as well? Some stuff with matrices? Yeah. Differential equations, you guys do a little bit as well. So you're not stunned by this word matrix that I've mentioned, right? So we have heard of matrices before. Okay. Well, no, not a big deal. I'm gonna show you what I need you to know, right? Not assuming too much previous knowledge, but some previous knowledge obviously helps a little bit. So a matrix is some sort of array of numbers, right? Usually be like a couple of columns and a couple of rows. You could have a matrix like that. You could have a matrix A, B, C, D like that. Although generally a one-dimensional matrix is called a vector. All right. So if all your numbers are just in one row or one column, all right, you can have a big matrix like A, B, C, D, E, F, and on and on and on. Okay. So there's many different, any combination of columns and rows is how you can express a matrix. Right? Matrices are very useful for us in chemistry. One in particular would be a matrix that represents the x, y, and z, or it's more a vector then. It's the coordinate vector of an atom in a molecule. Right? Z or 7Y? Oh, it should be a Z, thank you, yeah. That should be a Z, X, Y, Z, yeah. Okay. So if we can imagine putting a molecule like water, O, H, H, right? Okay. I'm going to label my H's 1 and 2 so we can distinguish them. If we can imagine this water molecule being imprinted on X, Y, Z space, okay, X, Z is generally going to be what a lot of people have traditionally thought of as Y coming into a course like this, because we like to just draw space flat on our board. But now Z is generally going to be the vertical axis of our molecule, okay, especially if it's the highest Cn that we talked about the other day. All right? And so then Y would be coming out of the board. So, when you've got a coordinate system like this, you could say, oh, what's the position X, Y, Z of that hydrogen atom or of the oxygen atom? In that case, it's 0, 0, 0, right? So we could have a vector that lists out those three coordinates for us, right? We would do that then because every symmetry operation has, or every symmetry operation, the ones that we talked about the other day, can be described as a matrix, maybe not as, but as a matrix, multiplied to the coordinate vector of, or these should be coordinate vectors of the atoms of a molecule. Okay. I'm going to show you this, but so if we took water and performed the action of a C2, right? C2 is 180-degree rotation. After that, C2, right? How does water look? Well, it looks the same, right? Which is why this is a member of the point group. That's why this is an operation of this group. However, our hydrogen 1 and hydrogen 2 are now replaced or switched places. Okay? So the coordinates of hydrogen 2, its x value is now negative x. Right? See, it was over here in positive x territory. Don't know how far, but but the bond lengths are equal, so now it's over here on the negative side, right? Okay. How has the z coordinate of this hydrogen atom changed? It hasn't. Okay, it hasn't. It's still, z is this dimension now, right? So z is still the same. Okay, we skipped y for a second there. Now, how has the y coordinate changed? For water, it doesn't look like it has changed, okay? But because it's in the plane. So water's not the best example to show this. But if this hydrogen was out front of the board a little bit, now it would be back behind the board due to 180 degrees. So its y, if it was positive y before, would be negative after the rotation. So both the x and the y become negative upon doing the C2 operation. Okay? And with a simple molecule like water, it's hopefully easy to see what I just talked about. Okay? Or an ammonia would be helpful there too. Okay? So the goal now is, can we figure out how a matrix and how a matrix multiplication would have predicted this? All right? Because if you can predict it for a simple molecule like water, then you can use that act when you can't draw a simple little picture. All right, so we want to teach ourselves, prove in theory what we're doing, or in idea, concept to ourselves what we're doing, so that then we can apply it to situations where we probably can't work it out just on a simple drawing like we have with water here. Okay? All right, so now before I can show it to you, we have to know a little bit about matrix multiplication. Again, not knowing exactly how you've seen this before. I'm going to do a matrix A, B, C, D. Okay? And I'm going to multiply it by a different matrix, N, M, P, Q. Okay. The key to matrix multiplication is that matrix 1 must be as wide as matrix 2 is tall. Okay? Matrix 1 must have the same width as matrix 2 has height. So really this is saying you must have as many columns in matrix 1 as you have rows in matrix 2. But students sometimes get lost in that. So width must equal height. Right? The way to multiply is that you're going to take a row times a column, and you're going to do the respective positions. So A and N and B and P. So my first entry in my new matrix would be A times N plus B times P. Now when we put numbers in here, it'll just be a single number. But for now. Okay? To get the second entry in the first row, see, when I work with the first row in the first matrix, I'm always producing the first row in the product. When I work with the first column in the second matrix, I'm always producing the first column. Just remember, the rows from 1 and the columns from 2. Right? That's what goes together. So now, to get the second position, I would take A times M plus B times Q. And then in my bottom row, I would have C times the N plus D times the P. And then C times M plus D times Q. That's how it would work out. All right. So let's say we had a 2 by 3 matrix, 2 columns by 3 rows. Okay. So we can multiply this by a matrix that is only 2 tall. Okay. And it can be as wide as we want. All right. So let's go with how about 5, 2, and 4, and 7 again. Okay. So the product of this matrix is going to be two columns wide, but 3 rows wide. It's going to be just the same size as this first one here. Okay. So our first entry is found by taking the first row times the first column of the second matrix. So 4 times 5 plus 1 times 2. So 20 plus 2 is 22. Then we take the first row and go to the second column. 16 and 7, 23. Now we just repeat, moving down to the second row. 30 and 14. What's that? 44. 24 and 49. So what's that? 73. And then the last one, 10 plus 6, so 16, and 8 plus 21, so 29. So that's the product of these two matrices that we have here. Okay. And yes, I know that there's plenty of software that'll do this for you. Won't be letting you, use that on your test or anything. All right, if you should need to do that. But on your homework tonight, I would hope you would be trying to actually practice the skill rather than, entering these just into a computer. For me, I think it takes longer to enter all this stuff into a computer than it does to actually do what I just did right there. Okay, I believe it would take me longer to sit down to a computer, open up the program, type in these two matrices, and tell it what to do. Okay, so this is a lot easier. All right. So how can this help us with our water molecule? Okay. So we started with a hydrogen 2 atom, right? So our H2 atom had these coordinates, x, y, and z. And then after the rotation, the new coordinates we found were negative x, negative y, and z. So the question is, what kind of matrix exists that we could multiply by this vector to produce this over here? Okay. So can we figure out how big this matrix needs to be? Our matrix 2 here is 3, right? 3 positions tall. So that tells us that our first matrix needs to be 3 positions wide, right? 3 positions wide. That's the only way to multiply these things is 1, 2, 3, 1, 2, 3. Okay? All right. And now, does it have to be 3 tall? It does, so that you have 1 position, 2 positions, 3 positions. Okay? So to get this to be 3 tall, you need 3 over here as well. Okay? All right, so we need 9 numbers in this matrix here. So now this is good puzzle work here, all right? This value, negative x, right? I don't want to do this for every single position, but we need to take let's just think of it as a 1 by 1 multiplication. Okay. All right. Now, the only way to get this to give us negative x, right, is if the first number is negative 1 and the other 2 numbers are 0, right? Negative 1 times x plus y times 0 plus z times 0. It's the only way to get the y and the z to not contribute to the x value up there. Okay? And so our first row is negative 1, 0, 0. Now if we pick up on that, well, wait a minute. In the second case, it's this second row times this that's going to give us our negative y. So now we don't want any x contribution. So the first number is what's getting multiplied by x. So it has to be 0. Right? The second number is what's getting multiplied by y. We want it to produce negative y, so it's negative 1. The third number is multiplied by z, so it has to be a 0. In the bottom row, we want just z to track over here. So what's getting multiplied by x? Well, we want it to be a 0. What's getting multiplied by y? We want it to be a 0. What's getting multiplied by z? We'd like it to be a positive 1, so that the sign of z doesn't change. Okay? Now this would be really hard with anything other than a simple tracking of this to this, I admit. Okay? And this is not how we figure it out every single time. But this first case, it's not too bad. So what we see right here is what's known as the C2 transformation matrix. And every operation has a matrix like it. We're not going to make each of them the same way. But every operation has a matrix that would describe how it can act on the coordinates of an atom. And then what the new coordinates are after the operation. Right? So now I could pick any atom that undergoes a C2 transformation in any molecule. All right? Know what its coordinates are before. Multiply this matrix to the vector of those coordinates, and it'll tell me where that atom is afterwards. So it's showing me, it's transforming the molecule for me, okay, in three-dimensional space. Okay? And like I said, every operation has one of these. For rotations, okay, so for any Cn, the general form of these matrices, okay, I always mix up which ones. There's one that's negative, and I always mix it up, so I'm going to pull out, make sure I get the right one. The general way to get the values for any C3, C4 would be to take the cosine of the theta, the angle of rotation, times, or not times, but then the second position is the negative sine of theta, 0. Second row is sine of theta, cosine of theta, and 0. And the third row is 0, 0, 1. Okay. So for a C2, the theta is 180 degrees, right? Cosine of 180 degrees is negative 1. The sine of 180 is 0. So that first row becomes negative 1, 0, 0. Second row, sine of 180 is 0. Cosine of 180 is negative 1, 0. So you see this would predict this right here. Okay? And so every operation has one of these. Again, for rotation, you could now use this to predict the matrix for any other angle. 90 degrees, 120 degrees, you just plug in your angle, and this is going to give you the contributions there. Okay? All right. For reflections and some of the other matrices that we've looked at, all right? A sigma, a reflection. Okay? Depending on the, if it's a vertical one, okay? So a vertical mirror plane, okay, a vertical mirror plane here, like the xz, the plane of the molecule, all right, what would happen in that case is that only the y would transform. So you'd have 1, 0, 0, 0, negative 1, 0, 0, 0, 1. Okay? If we reflected a molecule in the plane of the board, okay, and this hydrogen atom, if it was out a little bit, when it reflected, it would get back. Its x and its z would stay the same, but its y is what gets changed. Okay? If this was a yz, then the x would be what changes. All right? And so there's that potential there as well. Okay? if we had, so that's called a sigma v, or sometimes that's also called sigma xz, okay, because you see that the y is what's changing there. Okay. All right. There is a sigma yz, which would be just the negative 1, 0, 0, 0, 1, 1, 0, 0, 1. Okay. Oops. Sorry. Second row is 0, 1, 0. Okay. So sigma yz, as I was saying, the x's would flip. The y and the z would stay the same. Okay. Water doesn't have this, but another common operation is the inversion operation. Okay. If you invert a molecule, this one actually might not be too hard to find. If you invert, every coordinate is now becoming the opposite of what it was. So you're going to have negative 1s down your diagonal and 0s in your other non-diagonal positions. So this would be the inversion matrix I. Okay. So pretty much we have all of these matrices figured out so that we can operate on the coordinates of an atom and predict where it will end up when the symmetry operation is applied to the molecule. Okay. But the group of the matrices for a molecule describes the entire behavior of that molecule when all of the operations are in play. Okay? And so for water, if we listed out the various operations of water, this is actually sort of table 4.8. Okay, so for water, which is in the C2V point group, okay, C2V point group, there are, as we just said, there are 4 operations. There's the identity, E. The identity matrix is just 1 on the diagonals, positive 1s on the diagonals. Okay. There's the C2 operation, which is the negative 1, 1. And then there are the 2 mirror planes. There's the sigma xz, which is 1, negative 1, 1 along the diagonal. And the sigma prime, or the sigma yz, which is negative 1, 1, 1 on the diagonal. Okay. So these 4 matrices describe everything that could happen to water. All right. Now, the 3-by-3 nature of these is really not coincidental when you start to think about it, because there are 3 coordinates, x, y, and z. All right? And it turns out, if we did more of what we did earlier with our x, y, z over here, we would see that the first row is always what's working on x. The second row is always what's working on the y coordinate, and the third row is always what's working on the z coordinate, right? Okay. But in all of these matrices, there are only values on the diagonal right here, okay? And what that means is that each resulting coordinate, right, the resulting coordinate over here only depends on the original x coordinate. In the case, to show you how that wouldn't be, if we looked at a C3, okay, if we looked at a C3, just for comparison, and I'll erase this in a minute because I don't want it to muddy the waters right now, but if we looked at the C3 transformation matrix, it would be negative 1/2, negative root 3 over 2, 0, root 3 over 2, negative 1/2, 0, 0, 0, 1. If this is now multiplied to an x, y, z coordinate, we're now going to have something times x plus something times y. So the new value of x depends on the original value of y to some extent. Same is true for y. When we go to figure out the y coordinate, something times x plus something times y, 0 times z. So the new value of y depends in part on the original x coordinate of the atom. All right? So here, x and y are interrelated. You can't change one without changing the other. Right? So you can't take an atom and only change its x coordinate. Right? If you change its x, you're going to also change its y, is what that's telling you. Right? So that's the contrast that I want you to see that lies ahead. But for right now, that's not true. A C2, x only affects x, y only affects y, z only affects z. All right? And in that case, we can what's called block diagonalize, which simply means make smaller matrices. Okay, ignoring the 0 elements. So we have, in this case, 3 1-by-1 matrices inside each of these matrices. Again, this first row is always about x. The second row is always about y. And this third row is always about the z coordinate. All right. All right. Now, there's two different things to do at this point. All right. One thing that we can do is to sum the diagonals of each matrix. So the sum of the E would be 3. Right? 1, 2, 3. The sum of the diagonals of the C2 would be negative 1. Negative 1, negative 2. This brings us back up to negative 1. The sum of sigma xz would be positive 1. And the sum of sigma prime, yz, would also be positive 1. This 4-number combination right here is what's known as a character, or the character. Okay? This is what's called the character of the C2V point group. It's just what we saw. It's the sum of, or the trace, the sum of the diagonal elements of each of these matrices. All right? And it contains, this is the set of characters. Okay? This is the set of characters. Each of these is respectively the character of its matrix. Okay? This is the set of characters of the C2V point group. All right? All right. Now, why is it important, and what does it do? All right? Well, it is actually a combination of, this representation. It's also called a representation of the group. It's really a combination. The 3, negative 1, 1, 1 is really the sum of three smaller representations okay? So what if I just focused on the x coordinate, right? The x coordinate, we got E, C2, sigma xz, sigma yz, okay, is 1, 1, 1, 1. This, sorry, it's not right. It's 1, negative 1, 1, negative 1, right? This is the sum of the x coordinate matrices. All right? What's important for x in each case? For y, it's 1, negative 1, negative 1, 1. And for z, that's the positive 1 all across the way. Okay? These three are what are known as irreducible representations of the point group. Okay? The 3, negative 1, 1, 1 is, quote, reducible. It can be broken down further, all right, because it's some combination of, in this case, these three all added together. If you add these three in their respective columns, look what you get. 3, negative 1, right? 1 and 1. All right? That's why we're saying this top one can be reduced. The irreducible ones each describes how, in this case, how a coordinate, okay, transforms, okay, upon an operation. Okay? Of all the operations, actually, we should say. It describes how a coordinate transforms under all the operations of the group. Okay? So this is telling us really the total behavior of what happens to the x coordinate, what happens to the y coordinate, or what happens to the z coordinate when we do all the stuff that we can do in the C2v point group. All right? All right. These irreducible representations, okay, these make up what's known as the character table of the point group. Okay? And the character table of the point group is going to tell us how any molecule that's part of that group, right, that we learned how to assign things as part of the group last class, how it behaves under all the possible operations that exist. Question?
The irreducible representations, those are the 3, negative 1, 1, 1 up top?
Yes, these are okay. These are the irreducible representations. This one is reducible. Okay? Reducible. Okay. All right. Now, other side of your chart, or your handout, table 4.7. Table 4.7 tells us the rules of every point group. Because as it turns out, these three things right here, one is missing. There's a fourth one. There should be a fourth representation that describes how water or any other molecule, all right, that is in the C2v point group, how it's going to behave or how it can be transformed. Okay. So, and how do I know that? Because of the rules that are laid out here in table 4.7. All right, so if you have that handy, let's look at the rules here. Okay. First of all, we talk about the order of the group. order of the group is given the symbol H. Basically, it is just equal to the number of classes of operations. Okay? Number of classes of operations. Okay? So in the C2V point group, we've got E. That's an operation. We have C2. That's an operation. Sigma and sigma prime, they are unique operations because one is a plane this way and one is a plane this way. All right? And so they're different classes of operations. So there are 4 different things. So that's the order of the C2V point group, for example. All right? Now, symmetry operations are arranged in classes. As I already said, all operations in a class have identical characters. All right? That's not super important, but that would be if you should find multiple C2 axes in a molecule. All right? They can all be grouped together, all right, if there's no distinction between them. All right? All right? The third rule, the number of irreducible representations equals the number of classes. Okay? And that's how I knew that there should be a 4th irreducible representation in my thinking of all the transformations that can apply to water here. Because there are 4 classes up here, so we have to have 4. This means that all character tables are square. They have as many columns as they have rows. All right? That's the natural outcome. So all character tables are square. All right. Now, the other rules are really going to help us figure out what the missing, irreducible representation would be. I'm going to skip those for a second, and we'll go down to the bottom rule, which is one that should be looked at pretty quickly. Every group, every point group, has an all-symmetric operation or representation. So that means all ones. We already have it. Our z coordinate is entirely symmetric, all right, in the C2V point group. Nothing changes the z coordinate, all right. So we already have that. But sometimes that's an easy way to get a representation that might be missing from any group that you're looking at. All right, if you're looking at an impartial thing. Okay. All right, now let me explain some of these other rules, 4, 5, and 6. So they're presented in the rules 4, 5, and 6 as sort of rules, but they can be used in reverse to find missing representations. Okay, now, I'll try to show you that. All right. So rule number 4 is important. It says the sum of the E dimensions. So the sum of the numbers under E, the E dimensions, okay, squared. I guess I should really say the sum of the squares of the E dimensions, so you know where the square is applying to, okay, equals the order. Okay. So in the C2V point group, right, we have under the E, we had for the X a -1, sorry. For the Y, we had a -1, and for the Z, we had a 1. For our unknown, okay, value there, what we're saying is that the sum of these squared, -1 squared plus -1 squared plus 1 squared plus the unknown representation squared must equal the order of the group, which is 4 for C2V. So this is, obviously 3 plus our unknown value squared equals 4. So it's going to have to be that the unknown value squared equals 1, right? So the unknown value technically could equal plus or minus 1. Right? Technically, it could be plus or minus 1, right, at this point. However, okay, we're going to see that no two irreducible representations. Wait, I pulled the numbers under the C. Sorry, I pulled the numbers from under the C2. Maybe that's why I saw some looks. So these aren't negatives; they're just positive 1. Okay, all right, but still going to give us the same outcome. That E could be the E character of this unknown representation, this fourth one, could be plus or minus 1. Okay? But E pretty much usually is going to be positive 1. So, all right? If you don't see any other minuses, it's unlikely that's going to be minus 1. Okay? All right. The next rule is that for any irreducible representation, and then this wording is tough. I'm reading rule number 5 here. The sum of the squares of the characters multiplied by the number of operations in the class equals the group order. Okay? So if we go across a group, actually, I'm going to pull up a different, to show you how this works. Let me pull up a different character table. One that's not too bad. I want something that has some numbers in it here. A whole bunch of these are in the back of your textbook, the most common ones. So the D3 point group has the E operation. It has 2 C3 axes. Any molecule that's in D3 would have 2 C3 axes and 3 C2 axes. From this, the order is equal to 6. Okay? 1 plus 2 plus 3. Okay? Sorry, no, the order is equal to... Did I misdefine? It is 6, yeah. I think I misdefined the order earlier. I said the total number of symmetry operations. I said that it's equal to total classes. It's actually, just the total number of operations. So that includes the coefficients. So I don't like C2V as an example because everything is 1. And so it hides some of the coefficients that we might need to use. So I want to demonstrate this rule number 5 for you. So the order is 6. One of the irreducible representations of the D3 group, it has a label. The label is A2. The 3 values are 1, 1, and negative 1 in that. Okay, 1, 1, and negative 1. So the way Rule 5 is applied, the coefficient of E times the value of A, its representation, squared. Okay? Plus the coefficient 2 of C3. So this is the E coefficient. This is the E character. Sometimes it's called chi. All right? Plus then, this is the C3 coefficient times the C3 chi value, which is 1 squared, plus 3, the C2 coefficient, times negative 1 squared. Okay? That's the C2 character. So this equals 6 still. And again, sort of proof of principle here. Right? You have 1 times 1 plus 2 times 1 plus 3 times 1. So 1 plus 2 plus 3 is 6. But if you didn't know, if you had a character, a group that you, or a row representation that you didn't know all of its characters, right? For example, in this group, if there was one that had a value of 2, -1, and an unknown value there, we can use this rule to figure out this unknown value right now. So for this row, 1 times 2 squared plus 2 times -1 squared plus 3 times x unknown squared would equal 6. So you'd have 4 plus 2 plus x, or sorry, plus 3x squared equals 6. So 3x squared equals 0. Oh, we're done. X equals 0. All right, so this rule 5 is useful for finding one unknown member of the group, or of the representation, because of how this works. But you have to make sure you understand what you're doing is taking the coefficient, the number up here. There's one operation E. There are 2 operations C2. That's what this 2 is. There's 2 C3s, 3 C2s. That's where those 1, 2s, and 3s come from there. Okay? And sometimes the language there doesn't make a whole lot of sense. And then rule 6, so now that we know that this is 0, okay? Rule 6 tells us that any 2 representations are orthogonal. So if we took A2 times E, you take the coefficient times the character of your first representation times the character of your second representation. So you just work down the column. Plus coefficient of the second representation, okay, or second operation, times the character of the first representation times the character of the second representation. And then you repeat for C2, so that's 3 times -1 times 0. Okay? This would equal 2 minus 2 plus 0, so it equals 0. That's what Rule 6 says, is that any 2 representations are orthogonal. That means their product equals 0. The product, though, takes into account the coefficient. So that's the first value, the coefficient of the operation. The second value in your product is the character of the first representation, and then the character chi of the second representation. Okay? Again, it's the number out front of the operation times then the number underneath it and the number underneath it. It's really nice when they're right like this, but sometimes and when you look at a character table later on, you're going to see that they're not necessarily right next to each other. So it might be a little harder to find these 2 values, okay, because they're not stacked right on top of each other. Okay? Again, this rule doesn't seem to do as much right now, but if one of these values was unknown, I'm saying the 0 over here would be known. And so then if we knew this had to equal 0 and we had an undefined character in one of these representations, just like we found it up here, we'd be able to solve for the unknown. Right? So we have 3 rules, 4, 5, and 6, that let us solve for unknown characters in any of the irreducible representations. Sometimes they don't, it doesn't give you, like, we got X, obviously. But sometimes you have to build a system of simultaneous equations to allow it to happen. All right? And so it's a little bit frustrating. You have to sort of work your way up to what you're getting. Okay? So to come back to the water example that we were kind of working on then, if we applied these rules, we could ultimately find that there's this 4th missing representation. We found that its first number would likely be positive 1, all right? Because usually E, it doesn't change, all right? E, again, is the operation. It's not going to be changing the coordinates. And so it's going to be positive 1 and not negative 1, all right? In fact, I think there is a rule that says the E always has to be a positive. It can be 1, 2, or 3, but it doesn't have to be just 1, but it has to be positive, all right? And then we would sort of work our way up to the other ones. The fourth one, the one that's missing, I think was, we had, I can't remember now which ones we had, but the book works its way through it, but it becomes pretty obvious what you get, okay? All right, so now these character tables then, the full set of these representations, contain a lot of information about how any molecule behaves that's part of this group, right? And this is what we'll start to get into in our next couple of classes. Organic chemistry. You've all had organic chemistry. You've all done IR spectroscopy, right? Okay? The IR spectrum of a molecule depends on what point group it belongs to. Okay? And why some things are IR active and some things are not IR active. Anybody heard of Raman spectroscopy, right? Sort of like IR, but a little bit different, okay? All right? Again, whether you're Raman active or not depends on your point group, all right, and what symmetry elements you possess in your shape as a molecule, right? When you make something in the organic chemistry lab, how do you verify that you have it? What are some things that you did? You took an IR spectrum maybe, right? Took an NMR spectrum sometimes, right? Okay, looking for carbons and hydrogens, okay? There are various types of spectroscopy that we can perform that tell us where atoms are relative to one another and what's happening, okay? But in the organic chemistry lab like you had last year, you were kind of told, look for this. That's proof of a carbonyl stretch, right? Or look for this big whopping wide OH stretch in your thing, right? And if it disappeared, that told you your reaction happened. But what if you were sort of operating in a vacuum and there was no known spectrum, okay? What if you were looking for some kind of proof, something to say, I do believe I made my molecule, all right? This stuff is going to be able to predict how many stretches you should see or how many bends you should see, all right? So this is why it's particularly critical for sort of the idea of proving synthetic results, all right? And distinguishing between, another really important thing is distinguishing between isomers. Maybe you did a synthesis where you could have formed the cis and or the trans isomer of something, right? How do you distinguish between the two, all right? If you've got a pure one, their IR activity may be different. And all of it is predicted, believe it or not, by a lot of this stuff today. We didn't get anywhere close to done with it, all right? But a lot of it's predicted by that, okay? I have a homework assignment for you. Do not do the back. Do not do the back side of this, okay? We didn't get far enough to complete the back side of this sheet today. So just do the front side of this sheet for next class, and maybe we'll work through the back side as what we do to start class next time, okay? All right? Are there any questions about anything otherwise? Okay, so just the front side of this homework 4.2 that I handed out today, and I'll see you in class next time.